So we're going to stop. We're going to very quickly finish with Bernoulli percolation. I just wanted to mention one more thing about the understanding of the critical phase. This is because it might be useful later on, and also just I think it's good to know. So we mentioned a critical exponent, namely the fact that the probability that zero is connected to lambda n. If you look at this at PC, which here for on Z2 is equal to 1/2, we said that this is expected to behave like this, with alpha 1 that is a critical exponent. One arm exponent. And if I'm not mistaken, alpha 1 is supposed to be 5/42. I hope that I forgot to check the value. It just came to mind now. I think it's this, or 48 maybe. I can't remember. But it's a nice rational number. And what I claim is that much more interesting than computing PC is to find out this exponent. Why is that? Because you expect these systems to have what's called universality. So you expect that if you do Bernoulli percolation on any planar graph, the PC is going to depend on the graph. But you expect that if you look at that planar percolation at PC, you'll always have an algebraic decay for this kind of probability, and it's always going to have the same exponent here. And this exponent should be this one, which I'm now certain that it's not 5/42.
One just corrected it, it's 5/48.
Yes, it did look a bit strange to me, this 42. Right. So somehow what's more interesting than the value of the critical parameter is this picture of the critical parameter. By the way, this value here is obviously related to the Hausdorff dimension of that critical cluster that we've seen. But this isn't the only critical exponent. There are other critical exponents that you could look at as well. And you can write a whole list. There are standard quantities that should behave algebraically at PC. And you can write a list, the volume, the something. But I don't want to write them all. There are maybe 9 of them. I can't remember which are usually written. I just want to explain that there are exponents that also occur not at PC, but close to PC. And it's nice to look at both types of exponents. So remember, I wrote this, I drew this function for theta of PC, like this. And one thing you can look at is you can look at the way theta explodes here, like goes away from PC. And what you expect is that theta of P behaves in the vicinity of PC like P minus PC to the beta plus little o of 1, with beta positive as P goes down to PC. And again, this beta is expected to be universal, meaning it's going to be the same if you look at Bernoulli percolation on the square lattice, on the triangular lattice, by sides or by edges. On any kind of biperiodic planar graph, you expect it to be the same. It will depend on the dimension, though, but not, and on the fact that we're looking at Bernoulli percolation, or what's called the universality class of Bernoulli percolation. Okay, and finally, there's something called scaling relations, which is relations between these exponents. It turns out that basically, if you know 2 exponents, you should basically know all of them. Now, I only drew 2 exponents on the board here, so it doesn't really tell you much because you don't know what the other ones are. But I will explain to you, I'll give you another exponent and try to relate the 3. Again, I haven't really looked at this. I just thought about showing you this because I think it's interesting. So I haven't prepared the actual relation. I hope I'm going to find it on the spot. So another critical exponent that is very interesting is at PC, you have this sort of probability. So 0, you have here the box of size n, and you can look at the probability not as above to have one connection to distance n, but to have two clusters connecting to distance n, but two separate clusters. That means that these clusters will be separated by dual paths, like this. Okay? This is called a four-arm event. And it's equal to, it's expected to be equal to 1 over alpha 4. N to the minus alpha 4, where alpha 4 is also one of these critical exponents, and it's this one I know, it's 5 over 4. Okay, so here are three critical exponents, and what you expect, yes, what you expect is that they are related. So now, let's see if I can get it. Beta is equal to maybe alpha 1 over 2 minus alpha 4. I think. Okay, to be checked, but it's something like this. There's a relationship like this between alpha 1, alpha 4, and all other exponents. I apologize, I haven't prepared, so I might be making a mistake here, but I think it's this, the scaling relation. Okay, the surprising thing is that this is a theorem. By Keston from 1987, which is itself just based on the RSW. I mean, the core input is RSW for this. And what's surprising is that this theorem, when I say it's a theorem, it's not really true, because we don't know the existence of these values, beta, alpha 1, etc. We don't know the existence of them. We don't know their values. We don't know. We just know that these quantities do behave. These two quantities here do behave polynomially with lower and upper bounds that are of polynomial type, but you don't at all know what is the exponent or that there exists an exponent. And still, Keston managed to prove this kind of relation. Formally, what you should say is if the exponents alpha 1 and alpha 4 exist, then beta exists as well, and this. And actually, the quantities, this quantity, and this quantity, with different values of p and n, are related together. That's what.
Can I just ask one question on scaling relations? So,
yeah.
is this something that should only hold in 2D, or is it scaling relations in general meant to be the same in all D? Because the alpha 4, I don't know what the analog would be in higher D. That's why.
Yeah, so there are scaling relations that are supposed to hold in all dimensions. The proof is obviously completely out of yeah, I guess. I mean, maybe for other systems, there are other ways of doing it, but we don't have any chance of doing the proof for percolation. We don't know anything in higher dimension, unless maybe very high dimension. And the scaling relations, there's a dimension appearing in them, but other than that, they should hold, I think.
Alpha 4, the alpha 4, does it make sense in higher dimension?
Well, it should be the one it should be so alpha 4, what it governs, alpha 4 is the influence of an edge on an event, and it basically governs or decides the amplitude of the derivative of an event with respect to the one edge. So in higher dimension, it should be just something like, if you look at crossing probabilities, which maybe is the intuitive thing to look at, it should be the probability to have two clusters coming close at a single point, at least below dimension, below the upper critical dimension, because there, I think you start having crossings behaving differently, so maybe things are changed.
Thanks.
But yes, I think it's something like two clusters meeting at a point. Right. So I just mentioned this. If there is interest in this, we can come back to it later on. Okay, so now let's talk about very briefly about FK percolation. Maybe just show of hands, who knows the definition of FK percolation? Okay, so there's quite a high number, I think, if I see correctly, but I'll give a brief
I can maybe
introduction.
tell you. So can you just do that again? I would say like
Don't be shy.
2/3 of the room.
Okay. So I'll go through it quite quickly and I'll explain what is interesting to me in FK percolation. So the setting, we're in a finite subgraph of Z2. We're again dealing with the open and closed edges. Finite graph, I'm going to also define the boundary, which is just the vertices that have neighbors outside. And when you look at FK percolation, what you're doing is you're basically doing Bernoulli percolation, which means that the probability of a given configuration is this, p to the number of open edges, 1 minus p to the number of closed edges. But then you want to include some dependency between the edges. And the right way of doing this, for reasons that I'm not going to go into, is by adding a sort of weight here. It's as if you weigh Bernoulli percolation by an additional factor, which is q to the number of connected components or clusters. Now, when you do this, it makes sense because you're looking at this system as being part of a larger system to count the connected components using also connections that are potentially outside of your graph. So you do this by introducing boundary conditions, which encode connections outside of your graph. Formally, a boundary condition is a partition of your boundary vertices. And when you count the clusters, what you do is you merge all clusters that are in the same, if they're wired via boundary conditions. So here, for instance, in this picture, with these boundary conditions that I've drawn here, this connected component here and this one here is the same one. It counts as a single one, and this one here as well, and so on. This one here as well. Okay. However, notice that there are other connected components. This is a separate one, and all of these are also separate connected components. So I don't know how many there are here, but you count them and you put Q to this number. And because you do this, as you sum these weights, the red multiplied by the blue, you don't get one, as you did before. If you didn't have the Q to the number of clusters, you wouldn't need to do anything else to have a probability measure. Now, if you want to have a probability measure, you just have to renormalize here by what's called the partition function, which is just the sum of all these weights over all configurations. And you can do all of this because you're in finite volume in a finite graph. There are finitely many configurations, and you define this kind of probability measure. You observe that if Q is equal to 1, then you obtain Bernoulli. And we're generally going to look at Q larger than 1 for a reason that I'm going to explain in a minute. So there are a few properties that you should know about FK percolation. The first one is the spatial Markov property, which is not at all surprising. It's been developed, like the model is designed to have it. So the setting is the following. You take H, here a subset of a bigger graph G. You condition on the configuration outside of H, and you wonder what's the configuration in H here. And it turns out it's not surprising. It's just a configuration in H. It's just a model in H with the boundary conditions that are induced by the connections outside. So for instance, this vertex and this vertex in the boundary conditions, they are disconnected, but this vertex and let me see which other, this vertex, these are connected because they're connected via here, like this. Okay, so you take these boundary conditions and that's what you get. That's the marginal of this conditional measure in H. Okay. There are certain boundary conditions that are particularly interesting, which are what's called wired boundary conditions and free boundary conditions. Wired is everybody is connected together outside, and free is nobody's connected outside together. Okay, these are somehow extremal, and I'll explain why. And we call them 0 or 1. There are standard properties of FK percolation. Because Q is larger than 1, which is really important for us, you have this FKG inequality, the same as before. Positive, increasing events are positively correlated. So if you know something that means that there are open edges, then you have more chances of having open edges elsewhere. Somehow, this is more or less what it means. It's essential that Q is larger than 1 here. You have monotonicity of the measures, meaning you have monotonicity in the parameter P. This is something that we've seen for Bernoulli percolation. And you have also monotonicity in the boundary conditions, meaning if you take the model with a boundary condition and another boundary condition which has more wirings, then there are more open edges in it. And you have simple bounds by Bernoulli percolation. Now, I'm going very fast here because I see that most of you are used to it. If there are any questions about what it means to have one measure that is smaller than another, please let me know. It essentially means that you can couple the two measures or the three measures here in such a way that the configurations are increasing almost certain. Okay? Let's do a little computation. Let's look at the graph and the two boundary conditions possible, the free and wired boundary condition. And the graph is going to be surprisingly simple. It's going to be just this graph. A line. A single edge. What is the probability that a single edge is open? So what you notice is that if the boundary conditions are wired together, then whatever you do with this single edge, there's a single connected component. So if you look at these two weights, you get 1 over z 1 minus p times q. And if you look at E open, the probability is 1 over z p times q. And because of this, you can determine what z is. These are the two only open these are the only two configurations, and you notice that if in this setting, the probability that an edge is open is P. Okay? But this is not the only thing you can do with this graph that is a single line. What you can also do is you can consider the graph with free boundary conditions, so where the two vertices are not connected together. So you do the same computation, and what you notice is that there's a slight change. Namely, if the edge is closed, then now the graph has two connected components, so you should have a q squared here. Whereas if the edge is open, there is a single connected component. And so this gives you this different formula when psi is 0, meaning when the boundary conditions are free, meaning nobody's connected to, no boundary vertices are connected to each other. And you will notice if you look at this formula and you remember that Q is larger than 1, that you have an inequality, namely this one, which is a good news. It tells you that if you wire things outside of your graph, then it increases the probability for edges to be open in your graph. And so you see that Q larger than 1 was essential. You see that this is indicative of this FKG and positive association property and the monotonicity. And that's more or less all I'm going to say about it. It basically, this computation also shows you immediately this fact here. So from now on, think of FK percolation as a dependent percolation model. It has a lot of freedom, meaning each edge, no matter what the other edges do, it has still probability, a positive probability to be open and a positive probability to be closed. And edges help each other. Connections, existing connections help other connections appear. By the way, we're always going to look at this model as with a fixed value of Q and P varying. We're not varying Q continuously or almost never. It's actually different values of Q are different models. where it's different values of P are somehow different sort of temperatures. Okay, I'm going to go very quickly through how you define infinite volume measures. If you want to look at phase transitions and systems a bit like the Bernoulli percolation that we've seen before, it is quite standard to look at infinite volume measures, meaning measures not in a finite grid, but in an infinite grid. This was very easily done for Bernoulli because you could define them immediately there. For FK, it's a bit harder, but it's a standard thing to do. You can define them as limits of measures in finite volume. So you take very large graphs that increase to the lattice, and you take limits. Unfortunately, because of these boundary conditions issues, you could obtain different thermodynamical limits. But you can obtain at least two of them, namely phi 0 and phi 1, which are the limits as your graphs increase with free boundary conditions and wired boundary conditions. Both of these are invariant, translation invariant ergodic measures on configurations on the whole of Z2. And it turns out that they are almost always equal, but could be non-equal. So you could have, a priori, you could have phi 0 smaller, I mean, you always have phi 0 smaller or equal than phi 1, but you could have strict inequality a priori. But you can't have strict inequality many times. You have strict inequality only for at most countably many values of P. And this tells you that still your ordering kind of behaves well, meaning any increase, so phi 0, any infinite volume measure is sandwiched between phi 0 and phi 1. And any increase in the parameter beats any increase in boundary conditions. So if you increase the parameter from P to P prime, then the boundary conditions don't matter anymore. The measure with parameter P prime is always going to be larger than the measure with parameter P. Okay. And so you could have values of P for which these are equal, in which case you have a single infinite volume measure, or not. You could have measures for which these values are, for which the wired and free measure are not equal, and then you have a priori possibility of having more than, I mean, you have more than one infinite volume measure and a priori infinitely many. Okay, so I'm very, very quickly on this. These are classical things. Final thing, because we have this kind of monotonicity property, we can define a phase transition as we did for percolation. Namely, there exists a single parameter P such that the model transitions from having no infinite cluster to having an infinite cluster. And when I say this, the infinite volume limits here don't really matter because of this ordering property. Okay, so there is a well-defined critical point. Right, and it's non-trivial because the model can be compared with Bernoulli percolation by adjusting the parameters, and the non-triviality of PC for Bernoulli percolation implies the non-triviality for FK percolation. And so just to understand a little bit where we are in the kind of global situation of what is known in Bernoulli and FK, maybe I should start by saying that Bernoulli percolation was introduced in the 50s, while FK percolation was introduced in the 70s. And here are a list of results for Bernoulli and for FK percolation. So subcritical sharpness, we've discussed this. It was done by Menchikov in 86 and by Eisenman and Barsky in 87, plus other proofs. For FK in general dimension. For FK percolation, the same proof was only done by Dominique Copin, Raufi, and Tassion in, I think it appeared in 2019. Okay, supercritical sharpness. I mentioned this. This was Grimet Marstrand from the 90s or from 1990. For FK percolation, this is remains still an open problem. Uniqueness of the infinite cluster. This is something that was done by Burton and Keene in 1989, if I remember correctly, and it carries over directly to FK percolation. And then if we look at 2D, the critical point in 2D was found by Keston in 1980 for Bernoulli percolation and was obtained only in 2012 by Dominique Copin and Befara. So this was the first proof. Since then, there are several other proofs. So what I wanted to show you is you see there is a large delay between the results for Bernoulli percolation and the same results for FK percolation. And this is not only due to the fact that it was invented a bit later, but it's really there are significant additional difficulties. Let me also finally mention the scaling relations. So that it's this link between the a priori unproved critical exponents. So for Bernoulli percolation, this was done in 87. For FK percolation, we did it, Hugo Dominique Copin, maybe 2020, I don't know exactly. Maybe 2020, let's put. And finally, you can think about whether the scaling limit exists or determine the critical exponents or really kind of show that there is something like a scaling limit. So this is an extremely difficult question. So I'll put here Smirnov 2001 for Bernoulli percolation, but this isn't a very general proof. It works in a very specific setting, namely site percolation on the triangular lattice. And for FK percolation in general, this is not at all known. Now, there is something that I should mention, is that there is a special value of Q, namely Q equals 2, which is related to the Ising model, which is very special and much more is known, maybe even more than for Bernoulli percolation. So I mean, not maybe, more than for Bernoulli percolation. So in particular, this thing is completely well understood, very well understood for Q equals 2. Okay, so we're gonna kind of be around this part. This is our domain in this talk. I mean, this. Are there questions for? Huh? Okay, so what I want to prove to you now is and show you is how also for Bernoulli percolation, PC is equal to the self-dual point, and how the phase transition of Bernoulli percolation is really richer and has more, of FK percolation is richer and has more features than that of Bernoulli percolation. So I hope it's clear, FK percolation is not different from Bernoulli percolation. It's a large generalization. So it's a family of models. Bernoulli percolation is one of them, and it's an uncountable family of models, which are all expected to behave differently at the point of phase transition. So let's go back to duality, and from now on we fix 2D. You remember what the dual model is. For reasons that will become clear a bit maybe tomorrow, I sometimes draw the lattice turned by 45 degrees. So here we have the primal, on the left. And here in blue, we have the dual. And I claim that if you sample a configuration on a primal graph and then take its dual, the dual will have also a FK distribution with the same value of Q. Obviously, this FK distribution will be on the dual graph. It will have dual boundary conditions. And what's most important is it will have a different parameter P, and the parameters P and P star are linked through this equation. What it means to be the dual the dual boundary conditions. So how do you pass from psi to psi star? I don't want to get into this, but basically everything that is wired translates to free and everything that is free translates to wired. It's kind of intuitive. The one thing you should know is that if one is completely free, then the other one is completely wired. And then I'll explain to you whenever we reach a point where we do this for simple boundary conditions like this, I'll explain to you what it means. And so the first thing that you do when you see this kind of equation here is you wonder, when is P equal to P star? Because you expect this to be a special point. And this is called a self-dual point, and a simple computation shows you that it's square root of Q1 over 1 plus square root of Q. And you notice that if you put Q equals 1, you do get 1/2 that we had before. So for Bernoulli percolation, it is the self-dual point of before. This isn't surprising. It's obvious that that's what you are going to get. Okay. So if we trust our intuition from Bernoulli percolation, and if we trust that basically there is one point of phase transition where the model changes its behavior, it needs to be this point. So nobody's going to be surprised if you tell them that the self-dual point is the critical point. But some people, until 10 years ago or 15 years ago, would have been very surprised if you told them that you proved it. So we're going to prove this, and we're going to prove much more about the phase transition, actually. We're a bit like in Bernoulli percolation. We're first going to look at the self-dual point and understand this point very well, and only after we're going to maybe deduce in passing that it's the point of phase transition. And so what we're going to do is that we're going to prove that there are two possibilities at the self-dual point. Two possibilities related to the RSW property. So possibility number one, which I will call a RSW regime, or an RSW regime, is the following. Is if you look at the probability of having a circuit in an annulus, you remember this RSW was telling you that this has uniformly positive probability. So this probability is uniformly positive. Oh, sorry. It's what's written here. Both for the primal model and for the dual model. But what's most important, and this is the key, is in adverse boundary conditions. So you'll notice that what I'm claiming here is that there exists a positive probability of having a primal circuit even when the boundary conditions are the worst possible boundary conditions, meaning free boundary conditions. And vice versa, there's a positive probability of having a dual circuit even in the worst boundary conditions for the dual, which are the best for the primal, namely wired boundary conditions. So this is the RSW regime. And it's really essential that you work with these adverse boundary conditions. And if you don't have this at the self-dual point, then what you're going to have is you're going to have the boundary conditions that completely determine how you behave. And you have this kind of regime of exponential decay in adverse boundary conditions. So what I mean is, for instance, here, even if you put free boundary conditions extremely far from you at infinity, they still influence what happens locally, and they influence it very strongly. Essentially, you're in a subcritical measure. Phi 0 is behaving like a subcritical measure, meaning it has exponential decay of connection probabilities. Whereas phi 1 behaves like a supercritical measure. It has exponential decay of probabilities for the dual, which gives you all these properties of supercritical behavior. So this is a regime, this second regime is a regime where phi 0 is different from phi 1, and they're different because they're basically, one is supercritical and one is subcritical. Okay, this is what we're going to prove at the self-dual point. And as a consequence of this, we will obtain that the self-dual point is PC and that the phase transition is continuous. And here, let me just draw two pictures of how these things would look at the self-dual point. So in the RSW regime, which is going to be here on the left, if you put a box with, say, free boundary conditions on the sorry, I had them in red all the time, wired boundary conditions at the top and free boundary conditions at the bottom. Maybe I should draw these in blue. I don't know. Then you could define an interface between the wired and the free, and this interface would be something like this. So blue is the dual model, okay? I can't draw. Normally I draw dotted lines for the dual, but I can't. So you'd have an interface that is something like this. And then in the top, you would have blue bubbles, which are fractal. They're of all sizes. And in the bottom, you would have red bubbles, and so on. So this is typically what you would see when you're in the RSW regime, and you'd expect this interface to converge in the scaling limit to an SLE curve of a certain parameter kappa, with kappa that is dependent on Q. It really does depend on Q, so they're different for different values of Q. And I have the formula, but I can't know it by heart. And what do you have in the other regime, namely when phi 1 is different than phi 0? You have a very different picture if you force the existence of both primal and dual boundary conditions. So if you put yourself in what's called a Dubrusian domain, which is this, what you're going to have is you're going to have an interface between the free and the wired. But these guys, they really, really hate each other. So they really want to spend the least amount of time possible together. So what they'll do is they'll have a basically straight interface like this. The top part will behave like a supercritical measure. So it will have very small pieces of blue, of dual. And the bottom will have very small pieces of red, like this. And if you're really into it, you can look at this this interface and notice that it has a Brownian motion-like behavior at scale square root n, where n is the diameter of your box. So it basically it will be extremely localized around the straight line. It will have variations of order square root n, and if you zoom in, it's going to look a little bit like Brownian motion. This is not proved yet, but almost. Are there questions about this? Okay, so if you're looking at the critical phase, you're really interested in this behavior. This is the behavior where there's a single measure at criticality. Phi 0 is equal to phi 1 at criticality. Maybe I should have said it. So here in the phi 0 is equal to phi 1 at B self-dual, which turns out to be PC. And it's the only time where you have a critical measure that is supposed to have this fractal behavior. In this other regime where phi 0 is different from phi 1, you're basically, if you would imagine that you have a movie where you increase P from subcritical to supercritical, it's as if you skip the whole critical phase. You really jump over. It's as if you're increasing P like this, you blinked, and you already found yourself in the supercritical phase, and you just skipped both criticality and the neighborhood of the criticality. So here, there's nothing much to say about the critical measure. It doesn't exist. Okay. Yes, I'm way too late, so I'm gonna stop. I wanted to prove to you this theorem, but I think maybe we'll try to do that tomorrow, or not. But maybe just let me just get back to the theorem and just tell you. So it's a very powerful theorem. It kind of tells you these two ways of behaving, and there are a lot of other conditions that are equivalent to either the first or the second. There are really two different types of phase transitions. It was first proved by Dominique Copin-Sidorovicius and Tassion in 2015, and then in a more general setting by Dominique Copin and Tassion in 2019. And the theorem doesn't tell you which of the two situations you're in. It just tells you these are the two possibilities. And it's very interesting to try to decide where you're in. And what I wanted to do afterwards, after I proved to you this theorem, which I failed to do today, I wanted to show you that we can decide in which setting we are. So the answer probably for those of you who've seen Trisha's course is not surprising. When Q is between 1 and 4, you're in the first case. And when Q is larger than 4, strictly, you're in the second case. But this isn't contained in the theorem somehow. It's a separate thing. And you need a really separate ingredient that will tell you in which one of the two you are. But because you know that these are the only two possibilities, it kind of separates, doesn't leave any middle ground. So even a very weak indication that you're in one or the other of the cases is enough to determine in which case you are. The theorem became very influential. It was replicated in other settings as well since. So it's something we do expect to be somehow universal. And I think it's valuable to understand well this kind of problem. But I think I'm going to stop here. Is it correct, Trish?
I should? Yeah, that's yeah.
Okay.
Excellent. Let's thank. So, any questions? Also on the online, if you have any questions.
Yes, somebody wrote 5/48 and nothing else.
Okay, so if there's nothing else, then let's resume again tomorrow afternoon. So thanks again, Mano.
Yeah. Sorry, you said tomorrow afternoon, but actually you don't.
Yeah, Indian time, right? So for you, it's 2:15. Sorry. It's that's my bad. That was a critical mistake. It's 11:30. That's on the schedule. It's 11:30. Sorry, that's my bad. Yeah.
Okay, so we're staying with 11:30. Yes.
Yeah. So 11:30, and then the final one will be after lunch at 2:15.
Okay. Thank you all.